This chapter is about thermochemistry, so we need to talk about thermodynamics, which is the study of energy and its interconversions, and this affects matter, so that's why we're interested in it for chemistry. So the first law of thermodynamics is sometimes stated as there is no free lunch. And you may say, well, but I got free lunch when I was in elementary school. Was that lunch free? No, taxpayers paid for your lunch, right? You didn't pay for it, but somebody paid for it, right? So the more scientific statement of the first law of thermodynamics is the total amount of energy in the universe is constant. And what this means is you can't design a system that will make more energy than it consumes. So with energy, you cannot get something for nothing. All the energy that exists is all the energy that exists. And you could pull it in from different places. And if you take Chem 1B, you'll learn the second law of thermodynamics, which is not only can you not get ahead, you can't even break even. Because every time you do a transition of one kind of energy to another, you lose some to what's called a heat tax. So every time you do something with energy, you lose some to usefulness. It's still in the universe, but it just dissipates as heat. Maybe that's where global warming's coming from. That's an interesting idea. Anyway. Okay, so when you talk about state functions, so we're going to look at mountain climbing, because that's related to chemistry. So here's a mountain, and there's two paths. So you can go up path A, which is like more of a regular trail, a lot of switchbacks and stuff. And the trail itself is 12 miles long, and you're going to go from the bottom at 0 feet to the top at 10,000 feet elevation. Or you can do the crazy thing and just go straight up the side of the mountain, right? Harder, but shorter, right? So 5 miles straight up, but yikes, that's a hard 5 miles. You're still going from 0 feet to 10,000 feet. So when everybody gets to the top, their change in elevation is the same regardless of how they got there. Doesn't matter how they got there. You know how I would get there? I'd call a helicopter. I'd be standing over here, have the helicopter pick me up. We go up here and over here and land me right there. Elevation change is the same. A state function does not depend on how you got from point A to point B. The distance that people travel does depend on how they went, but the change in elevation does not. Does that make sense? So it's a state function. Because we're going to talk about things that are state functions and things that are not state functions. Lots of definitions in this chapter. So the internal energy, symbolized with a capital E, of the system is all the kinetic and potential energy that the particles in the system have. You just add together all the potential and kinetic energy. So internal energy is a state function. The internal energy of a system only depends on what it is, not on how it got there. Okay? Doesn't matter how you got there, it's just what you've got. So we can look at the change in internal energy, and this triangle is a capital Greek delta. So we say delta E, and delta always stands for the change in, which is always the final amount minus the initial amount. It's the final minus initial. So the change in internal energy can be determined by looking at the energy that it has in its final state and subtracting the energy that it had in its initial state. And that also is a state function, doesn't depend on how it got there. So this is delta. Change in final minus initial. And you'll see that that's just consistent all the way through Chem 1B, at least. So this is what's called an energy diagram. And so you can think of this a little bit like that elevation diagram with the mountain, right? So here, going up, internal energy is increasing. The mountain picture, elevation was increasing, right? So here we have carbon and oxygen. Those happen to be the reactants in this balanced chemical equation. And these have higher internal energy than carbon dioxide has. We're not going to go into why that is. It just is, okay? So these have higher internal energy, and this has lower internal energy. So in the process of this reaction occurring, to find the change in energy, we're going to look at the energy of the products, the final thing, minus the energy of the reactants. So we're taking this lower, smaller number and subtracting a bigger number, and we get a negative number, right? So the change in internal energy, delta E, is negative. It's less than 0. Because we started up here and we went down. So if you think back to the mountain, if I started at 10,000 feet and I went down to the bottom, my elevation change is negative 10,000 feet, right? Because I was going down. There's directionality here. When I start at the bottom and I go up, final minus initial is positive 10,000. So the change in energy for the reaction is the energy of the products, the end, the final, minus the energy of the reactants, the initial. Okay? And so what happens here, the system is losing energy. Where does the energy go? It goes to the rest of the universe. It goes to the surroundings. So it's negative for the system, it's positive for the surroundings. Reactants have more energy in this example, so we have energy being lost by the system. The energy lost by the system is gained by the surroundings. So delta E for the system is negative, delta E for the surroundings is positive, but the absolute value, the magnitude, is the same. And so mathematically we can say, well, delta E surroundings is equal to -1 times delta E system. This negative here does not mean that the system is negative. It doesn't mean that this is negative or this is positive. It just means that they are opposite in sign. Okay, we could take that equation and multiply both sides by -1. And then this negative and that negative would cancel out, and we'd have negative delta E surroundings is equal to positive delta E system. It's just one is opposite. So I find it helpful to think of energy as being a lot like money, because money is something we're all really interested in, right? We know about money. We buy things, we sell things, we want to figure out how to get more money. So this is like transferring money between accounts or from one person to another, right? If the system loses $10, then the surroundings gains $10. So it's negative for the system and positive for the surroundings. If the surroundings loses $100, it's negative, and the system is positive 100. It's the same number. The sign really depends on which side you are, right? Am I part of the surroundings or am I part of the system? But the number is the same. If we reverse the reaction, instead of making carbon dioxide, we're going to decompose carbon dioxide into its elements. Well, carbon and oxygen still have higher internal energy than carbon dioxide does, just because that's how it is. But now this is the initial state, and that is the final state, because we're doing it backwards. So final minus initial is going to be a positive number. So energy is coming into the system. Where does the energy come from? It comes from the surroundings, because it has to come from somewhere, right? If I transfer money between my checking account and my savings account, one loses, the other gains, right? If I deposit money at the ATM, my bank account gains and my wallet loses. If I sell something, I gain money from you and you lose money, right? Money doesn't come out of nowhere. Energy doesn't come out of nowhere either. So this is a summary of what we've been talking about. If we're starting with higher energy and ending with lower energy, that is energy loss. It flows out of the system. If the reactants are low in energy and the products are high in energy, then energy is coming into the system, and delta E system is positive. So this change, you can think about like, well, what would that look like on my bank account balance? Did I gain $10? That shows up as plus 10, right? Did I spend $100? That shows up as negative 100, right? So the energy coming in and going out is the same sign as money would be. So let's look at these imaginary internal energy gauges that are describing initial and final conditions. So this is the system and this is the surroundings. So this is at the beginning. The system is 3/4 full and the surrounding has a quarter tank of energy. Which energy gauges correspond to the final conditions following an energy change in which delta E cis is negative? So if the change in energy for the system is negative, does that mean the system is gaining or losing energy? It's losing energy, right? So this is losing energy. And what does that mean about the surroundings? It must be gaining energy. Is it gaining more or less than what the system lost? No, it's gaining the same amount, right? So we've got 3 different situations down here. Let's just start with C. So here we have 3/4 up to, 7/8 maybe, full. Is that losing energy? No. So that one's not right. About this one. We started at 3/4 of a tank, and now we're at half a tank. That's losing energy. What about the surroundings, though? It stayed the same. So that would imply that energy, was destroyed. Like money just, disappeared. Can't happen. So that's not possible. Here, our system is at half, and our surroundings are at half. So this one lost a quarter tank, and this one gained the same amount. So this is the correct one. Any questions? So energy can be exchanged between the system and the surroundings, and the way that that happens is through heat and work. Heat and work are not state functions. Their value does depend on the process. But what's interesting is the sum of heat and work is a state function and doesn't depend on the process. So we've got the system, we've got the surroundings. We can transfer energy as heat or as work. They can go in opposite directions and kind of cancel each other out. They can both go in the same directions. All kinds of things can happen. So we need to talk about sign conventions for heat and work. We've already talked about change in energy. So Q is the symbol for heat. Not sure why, it just is. Q. So if the system gains energy, thermal energy, then Q is positive. It's gaining heat. If it loses thermal energy, it's negative. right? So that's this really the same as delta E. It's just that we're talking about a particular kind of energy here. And then there's work, which is W. That makes sense. So work done on the system is positive. Work done by the system is negative. So let's say that your job is to give massages, right? So when you give a massage to someone else, you are giving out, right? You are expending energy to do this thing for someone else. You are doing the work. So that's a negative energy expense, basically. Work done on the system, you could think of work done for the system. This is, you are getting the massage, right? And that feels very positive, right? You're like, oh, this is good, this is positive. Someone is doing work for me, as opposed to I'm doing work for someone else, okay? So let's look at a pool table. Here we have a white ball rolling across the table and striking a purple ball. So this ball has an initial kinetic energy of 5 joules. As it rolls across the table, because this is a real table, there is friction, and so the ball slows down a little bit. It loses some energy, right? A ball on a pool table will not just roll forever. It'll slow down and eventually stop because of the friction. So it's losing energy through friction, which is heat, right? So if you rub your hands together, right, you start to feel warmth, right? The friction generates heat because it just is. I don't want to get into that. Anyway, so this is rolling across and it's losing heat. So it lost half a joule of energy rolling across. So when it gets here, it only has 4.5 joules of kinetic energy left. It gives those 4.5 joules of kinetic energy to the purple ball, and the purple ball goes running off. Now this one is at 0. So we can look at the change in energy for the white ball. Its final condition is 0. Its initial condition is 5. 0 minus 5 is negative 5 joules. The way that happened is that work was done. Hitting that other ball is work. And so that was negative 4.5 joules, because this one's putting out, right, doing something to somebody else. And we lost half a joule to the heat from friction. So the sum of these is equal to the total energy change. Any questions? So let's look at a rough table. Maybe this one's been, just like abused or something, or it's just like really, really old. And the felt is all kind of messed up. So the ball's starting out with the same amount of energy, 5 joules. As it rolls across this rough table, it's going to slow down more than it did on the smooth table, right? So think about taking a tennis ball and rolling it on the sidewalk or rolling it on the grass. It's not going to go very far on the grass because there's a lot of friction, right? So it's going to lose more energy as heat. So here it's losing 3 joules of energy. So over here now, it only has 2 joules of energy left for it to do work on the purple ball. So the purple ball still goes moving off, but now it has less energy than the other one did. Here our final energy is 0. Our initial energy is 5. 0 minus 5 is still negative 5 joules. The change in internal energy is the same, even though how it got lost is different between these two tables. It's a state function. Doesn't matter what happened in the middle. It's just the final minus the initial. But here, the work done was negative 2 joules, and the heat lost was 3 joules. So W and Q are different than they were for the smooth table because they do depend on the process. They are not state functions. Any questions? kind of already said this. So delta E for the white ball is the same for both the smooth and the rough table. Q and W are not. But when we look at the sum of Q and W, it's going to be the same, even though the individual values are different. Okay, let's apply that. A cylinder and piston assembly, defined as the system, is warmed by an external flame. The contents of the cylinder expand, doing work on the surroundings by pushing the piston outward against the external pressure. If the system absorbs 559 joules of heat and does 488 joules of work during the expansion, what is the value of delta E? First thing is always read the whole problem. And then we're going to highlight numbers, right? So we have 559 joules and 488 joules. Those are the only numbers in there. And then we're going to see, well, what are we trying to find? And the question word often happens, what? We're trying to find delta E. So let's pull out these numbers. So we've got 559 joules, and we've got 488 joules. So it says that this is an amount of heat, and the symbol for heat is Q, right? So that's Q. This one is that much energy of work, and so we're going to label that one W. Now we have to assign signs to these. Are they positive or negative? It's indicated in this problem by the words. So the system absorbs 559 joules of energy. My wallet absorbs $559. Is that positive or negative? Oh, it's positive. Cool, where can I sign up, right? The system does 488 joules of work. Is that positive or negative? I heard both positive and negative. Do you like doing work? No. So here it's doing work, right? You feel positive about that? No, we feel negative about that, right? I'm doing the work. I would feel more positive if someone else was doing the work for me. Does that make sense? Yeah. So this one's going to be negative. And those are really easy to mix up. And that's why it's like thinking about work in real life, right? It's okay to be lazy and want other people to do your work. And so we're trying to find delta E. There's an equation for that. So delta E is equal to the heat transferred plus the work done. So we have Q, we have W, so we have 559 joules plus negative 488 joules. (559) minus 488, and this is 71 joules. So the change in energy for the system is positive 71 joules. The system absorbed heat and it did work, but overall it gained 71 joules. What's delta E for the surroundings? Negative 71 joules, right? The system got, therefore the surroundings gave. 71 joules.